I am Dr. B. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. Today I am going to explain problems on diode resistance. And previously, we have discussed all theory topics regarding to analog and digital electronics. Now onwards, we are going to do some problems related to analog part and digital part. As we know that in this analog and digital electronic part, first two modules which are related to analog electronics. In the first module, all are deals with the diode and its characteristics and its applications. This second module is regarding to transistor and its applications and the operation of transistor. Now we will move to the problems on diode resistance. We know that as we start with this analog electronics with the concept of how to form diode. Once we form the diode, PN junction diode, we see that the characteristics of diode. There are two basic characteristics, forward and reverse characteristics. In the characteristic curve, basically we see that x-axis always represented with the volts, some volts provided by the external voltage, and what is the voltage provided to the diode, and what is the resultant current that flow inside the diode, which is measured in the y-axis. We know that we will get the curve. It may like growing like exponentially, exponential curve. So as initially it start with a slightly variation with the voltage, the current increases linearly, and once reach some certain voltage, like cut-in voltage greater than cut-in voltage, the current of the diode curve grows exponentially, increases. And this is about characteristics of the diode. So below the cut-in voltage, current flow. After cut-in voltage, exponentially current flow in the PN junction diode. And it is mentioned by that diode current. It is mentioned by ID is equal to the diode current is equal to I0 reverse saturation current flow in the PN junction diode, and e power V by eta Vt minus 1, where V is the supplied voltage, diode voltage, and eta is the intrinsic constant for material. Like if it is germanium, eta is equal to 1, and for silicon eta is equal to 2, and Vt is the volt equivalent temperature. So this current flow in the PN junction diode. Now the point is that the problems related to diode resistances, how that resistance exists in the PN junction diode. Whenever any element, the current flow in the current flow in that element, definitely there will be a opposition of the flow of current. The opposition of flow of current is nothing but resistance. So if it is not perfectly conductor, definitely there will be a certain portion of resistance existed inside the device. So here also diode also accepting the current flow. So when the current flow, by applying the voltage to the voltage across the diode, there must be a resistance. So basically there are two types of resistance, static and dynamic resistance. And static resistance is the ratio of the applied voltage by the current flow in the PN junction diode. Just R is equal to V by D, Vd by Id. If it is dynamic, we can measure from the graph. We will see that if it is a VI graph, the VI curve is like this. So there are two different ways to measure. Take the a tangential line uh, passing through the Q point, and the change in x direction, and the slope change in y direction dy did. And what is the dynamic resistance here? It is small rd is equal to reciprocal of the slope. That slope nothing but dy by dx. Slope is here, it is di by dvd. This is like y-axis point, y-axis changing point, changing value did, and x-axis changing point dvd, delta vd. So slope is nothing but delta id by delta vd, but dynamic resistance is nothing but a reciprocal of slope. Why reciprocal of slope means? So actually that slope is nothing but di by did by or delta id by delta vd. So it is I by d, I by v nothing but conductance. So v by I nothing but resistance. So reciprocally, if you reciprocal it, then we will get the resistance. So the dynamic resistance can be found from the VI graph, or d is equal to 1 by slope, nothing but delta vd by delta id. Then it is just delta vd and delta id, which will helps to find whenever there will be a graph and take the 2 points, so that we can apply, we can take the delta v nothing but subtraction of 2 points by delta id nothing but subtraction of 2 extreme points. So the changing values. But what if for problems? So we need to find the formula for dynamic resistance. We know that how to find the dynamic resistance. We have a diode current equation. ID is equal to I naught e power Vd by eta Vt minus 1. And from this expression, when we expand that I naught into equation, it will become like this. Then when we apply those differentiation, like slope, did by dvd for that above equation, for example, it is equation 1, we can apply the did by dvd, then we will get the equation on the right side, this one. When we apply the differentiation with respect to Vd to the equation on the right side, then we will get this equation, and then rearrange this equation, we will get that d, and then like a reverse of this, the above equation, dvd divided by delta id is equal to eta Vt by id plus I naught. So then we will take that this dynamic resistance, which is simply equal to dynamic resistance. Since ID far greater than I naught, diode current, when compared with the diode current, reverse saturation current I naught is very small. So by substituting that one, we will get that finally RD is equal to, indirectly, which is called what we call dVd by dId, or delta Vd by delta Id is equal to eta Vt by Id. Finally, we will consider that parameters which are existed in the diode. If Vt, when we are applying the power supply to the diode, and then we will we consider that thermal equivalent temperature inside the diode junction, and eta, it is regarding to diode material, and Id, the current flow which is exist in the p junction diode when we apply the forward voltage. So by considering all these parameters, three parameters, we will get the dynamic resistance. Whatever the problem given with that diode forward current with the apply of forward voltage, particular voltage, and what will be the dynamic resistance, like that. By considering all these three parameters, we will do the problem. Let us see that some problem, like we'll see a problem. And also here it is, remember that Vt, volt equivalent temperature, basically volt equivalent temperature Vt is equal to kT by Q, where K is the Boltzmann constant and T is the temperature in Kelvin, and Q is equal to charge of electrons or charge of carriers. So we will substitute Boltzmann constant and temperature, which is given by the problem, and then Q, we will get the Vt, or simply Vt is equal to T by 11,600 value, where T nothing but temperature in Kelvin. By substituting different temperatures, you will get different volt equivalent temperature. If you, for example, a standard value of T is equal to 300 Kelvin, 300 Kelvin, we will take directly that Vt is equal to 26 millivolts. By substituting T 300 Kelvin in the equation, you will get 26 millivolts. Directly, sometimes we need to substitute this value. Now come to let us see some problem. This is the problem. Find the value of DC resistance and AC resistance of germanium junction diode at 25 degrees Celsius with the reverse saturation current I0 is equal to 25 microampere and at an applied voltage of 0.2 volts across the diode. If you see carefully about this problem, find out the DC resistance. We know that we have two resistances, AC and DC resistance. DC resistance simply ratio of voltage by current, and AC resistance we know that we have a formula, small r is equal to eta Vt by Id. Let us see that. Of a germanium diode. So given data, if you see this problem, given data, so if it is a germanium diode, eta is equal to 1 for germanium. At germanium diode, the temperature T is equal to the applied temperature 25 degrees Celsius. Actually, in the formula, in order to find out Vt is equal to T by 11,600. T always measured in Kelvin. So we need to convert this degree Celsius into Kelvin. So T is equal to T in Kelvin is equal to 273 plus 25 degrees Celsius. 273 plus whatever unknown, like known temperature in degree Celsius, we can add, then we will get a temperature in Kelvin. So 298 degree Kelvin. This is actual temperature in Kelvin. Okay. And then reverse saturation current I0 is equal to 25 microampere. And applied voltage Vd is equal to 0.2 volts. Now, what is the need to be found? Find DC resistance and AC resistance. For example, dynamic resistance or AC resistance RD is equal to what? That is we need to find out. So when we apply these things in the formula, so small rd is equal to small rd is equal to eta Vt by Id. Eta is equal to 1. Vt is equal to, we don't know Vt, but we have a T. So first we need to find out separately what is Vt. Vt is equal to T by 11,600. We know, substitute this 298 Kelvin by 11,600. Approximately we will get 25 millivolts. If you substitute this one, you will get Vt is equal to 25 millivolts. So we know that Vt is equal to 25 millivolts, 25 millivolts. And what about ID? ID is nothing but diode current. We don't know. So they have given only applied forward voltage and reverse saturation current. So based on those given data, we will get that diode current. We know the diode current ID is equal to I naught into e power V by eta Vt or Vd by eta Vt minus 1 and I naught 25 microampere and e power Vd diode voltage applied voltage in forward bias 0.2 divided by eta 1 Vt 25 milli means 25 minus into 10 to the power minus 3 volts minus 1. By finding all the values into minimized into some values. So this can be written as this 10 to the power of minus 3, take the above 10 to the power 3, 0.2 into 10 to the power of 3, we'll get 2, like 200, e power 200 by 25 minus 1, you will get the value e power 200 by 25 means e power 8 minus 1. What about e power 8, 20, e power 8? So e power 8, you want to know. E power 8 the e power 8 value we will have 25 and 10 to the power of minus 6. E power 8 value is 2980, approximately 2980 minus 1. So we will get 2980 minus 1. So which is equal to 0.0. 74500 into 10 to the power of minus 6. Nothing but you will get approximately equal to 75 amperes. ID is equal to 75 amperes. This can be substituted into dynamic resistance. RD is equal to eta is equal to 1, Vt is equal to 25 millivolts divided by it is 74 milliampere, 75 milliamperes. $75 milliamperes. So milli cancel, you will get 1 by 3. So RD is equal to 0.33 ohms. The dynamic resistance for this diode is 0.33 ohms. So simply what we require is RD is equal to eta Vt Id. We must find out the Id separate based on the given parameters I0 and Vt, I0 and Vt and Vd, and then we need to find out a volt equivalent temperature Vt from the given temperature in Kelvin, and then substitute all these parameters. You will get RD, dynamic resistance or AC resistance. And DC resistance, we will directly find out DC resistance like small rd is equal to Vd by Id. Vd is equal to 0.2 volts divided by Id is equal to 75 milliamperes. So we will take the 200 by 75. We will take the 8 by 3. So 2 point something, 8 by 3. RD is equal to approximately 2.5 something. We will get the RD. So when we compare with the DC resistance, AC resistance should be small. Next, we will see that some other problem which is related to that regarding to diodes. Here it is PN junction. Germanium diode has a reverse saturation current of 0.110 or 0. We will take the 10. Okay. So 0.10 microampere. A PN junction germanium diode has a reverse saturation current 0.1 microampere at room temperature 27 degrees. It is observed to be 30 microampere improved when the room temperature is increased. Then what is the new room temperature? So it is basically formula which is required for this problem is the reverse saturation current I02 when temperature T2 is equal to reverse saturation current I0 when temperature T1 into 2 power T2 minus T1. The T2 minus T1 is equal to delta T, change in the temperature. So we have given parameters I01 like reverse saturation current when temperature 27 degrees, and it is improved. When temperature increases T1 to T2, then what is the observed reverse saturation current is I02 is equal to 30 microampere. Then what will be the value of T2? So I02 is given the improved reverse saturation current 30 microampere. I01 is given 0.1 microampere into 2 power T2 minus T1 is nothing but 27 degrees. So here it is, we can directly consider the degrees 27. So will we take this 0.1 microampere to the left, we will consider that 330 microampere by 0.1 microampere. 300 will get 2 power T2 minus 27. So 300 is equal to 2 power T2 minus 27. So what will be the T2? So when we apply log base 2 on both sides, you will take this T2 value. So T2 minus 27 is equal to log 3 base 2. So when we both sides apply the log base 2 and log base 2, 2 cancel, then you will get the T2 minus 27 on the left side, which is equal to log 3 base 2. We know that what is the log 3 base 2 is equal to 1.585. T2 minus 27 is equal to 1.585. T2 is equal to 27 plus 1.585 is equal to, what will be the new temperature? The increased temperature is 28.585. After 27 degrees, the current flow, reverse saturation current flow in the PN junction diode is 0.1. When that current will increase to 30 microampere, what would be the new temperature is 28.585. So that 1.585 improved in the temperature will be improved with 30 microamperes. So here it is actually T2 minus T1 by 10 divided by 10. So we will take this one into multiplied by 10, 15.85. 15.85. So we will get 32. 42.85. In this value, we take this, why this 42.85 means I2 is equal to I1 into 2 power T2 minus T1 by 10. This value, the temperature increase doubles, like temperature increase in every 10 degrees change in the temperature, it will doubles the current. So let us see that the temperature if we temperature increase 10 times, like 10 from the previous temperature, I1 into 2, T2 minus T1 is 10 times rise in temperature, every 10 degree temperature. So then the change in the temperature delta T is 10. The delta T is 10. 10 by 10 you will get I1 into T. I2 is equal to I1 into 2 means every rise in 10 degrees Celsius, change in 10 degrees Celsius, you will get doubles the current. It doubles the reverse saturation current for every 10 degrees Celsius change in the temperature. The same example, if you see this 10 microampere. 10 microampere to 20 microampere. So what is the formula? I2 is equal to, I2 means reverse saturation current at temperature 2, I1 into 2 power T2 minus T1 divided by. So I2 is equal to 20 microampere, I1 is equal to 10 microampere, 2 power T2 minus T1 is equal to 27 degrees divided by 10. So here it is, micro cancel, value is 2, 2 is equal to 2 power T2 minus 27 divided by 10. And we apply the log base 2 on both sides, T2 minus 27 divided by 10 is equal to log base 2, log 2 base 2, which is equal to T2 minus 27 divided by 10 is equal to log 2 base 2 is equal to 1. T2 is equal to T2 minus 27 is equal to 10. T2 is equal to 10 plus 27. T2 is equal to 37. Why I am taking this example means T1 is equal to, we have given 27, T2 is equal to 37. So when we increase our temperature in the graph, so T1 27, T2 37, when we increasing this temperature 10 times, like a 10 degree, every 10 degree temperature, degree Celsius temperature, from 27 to 37, the change in the temperature T2 to T2, T2 minus T1 is equal, delta is equal to 10. Then the rise in the current, reverse saturation current should be doubles. So here it is initially for 2 during T1 10 microampere. After increasing this temperature to 37, it will doubles 10 microampere to 20 microampere. So every 10 degree change in the temperature doubles the change in the reverse saturation current. Now, like no, I would like to show this one. So I want, so that's why I'm taken this 10 microampere and 20 microampere currents. So this is the way to find out the given temperatures. What is the effect of temperatures in the reverse saturation current? So sometimes it is, we need to find out, they have given T1, T2 and they have given I1, what will be the current flow. So I1 is given, T1 is given, T2 is given, T1 is given, then we need to find out I2. In this way we will find this P junction diode reverse saturation current with the two different temperatures. So these are the examples of problems related to diode, like diode resistance and the current flow in the P junction diode. So I have, in this I've been covered how to find out the threshold, the volt equivalent temperature, how to find out ID, how to find out dynamic resistance, how to find out static resistance, and how to find out reverse saturation current I02 for the given I01 and T2, T1. So these are some examples related to diode. So this These two books we found of these type of problems from the electronic devices and circuits, Jacob Millman, and electronic device and circuit theory, Robert L. Boylston, and our students will take these examples from the question bank of this analog and digital electronics course full stack. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.